Hi everyone, welcome back to the second module of this course on measurement and instrumentation, and we are discussing this analog meters, and we are in the fifth week of our discussion, and today we are going to discuss another kind of instrument which is known as electrostatic instrument. We have already seen the electrodynamometers, so we have now different kind of instrument. Of course, from the name you can say that it works on electrostatic forces. Okay, so the electrostatic instruments work on the principle of attraction or repulsion of electrodes which carry certain amount of electrical charges. Okay, so this is typical configuration of two different plates. Of course, this is not the actual electrostatic instrument that we want to study, but this is just to give you an idea that what we are talking about. Okay, so we have a fixed plate, for example, okay, and then we have a movable plate. Right now we are not seeing the, say, rotatory motion. Okay, right now try to understand this in the linear way only. Okay, so this plate I have hinged to certain point. Okay, and then I have another plate which can move at least to and fro, and there is a spring, okay, which is governing the, or which is controlling the, or trying to balance the force of attraction between these two plates. Okay, so I am using the word attraction or repulsion, not only attraction, so please note this word. Okay, so the electrostatic instrument, as I have mentioned, works on the principle of attraction or sometime on repulsion of electrodes which carry electrostatic charges. Okay, like you can see in this plate A and B, this is carrying positive charges, this is carrying the negative charge. Okay, so or we can say that the instrument works on the principle of simple electrostatic forces between two charge conductors. Okay, or there can be multiple charge conductors, so you can say that it works on the principle of electrostatic forces among different charge conductors. Okay, unlike the electromagnetic instruments, no current need to flow through the instrument for operation. Okay, so you have two different plates and there is a good amount of gap between them because they are carrying different charges. Okay, say this is negative and this is positive. Okay, depending on these charges you can have, say in this case for example, you can have a force of attraction. Okay, so if you see there is no current flowing from this instrument, rather than what we have is basically a potential drop. Okay, so we'll see that these instruments are basically used for measurement of this potential only. Okay, so these electrostatic instruments are mainly used for the measurement of high voltages. These voltages can be both, it can be DC as well as it can also be AC voltage. Okay, so till now you might be acquainted with these instruments, that in which case at least you can guess that if the instrument can be used for the measurement of AC or it can also be used for DC. Till now we have seen that, say, if the deflecting torque is proportional to, say, the electrical parameter, for example, say current, or say the deflecting torque is directly proportional to, say, voltage, these kind of instruments were working only for the DC, because we have seen this in case of different instruments. Okay, now when you have this deflecting torque directly proportional to I square, or say TD is directly proportional to, say, V square, we have seen that in these cases it is actually representing the average values. Okay, and we have mostly seen that in this kind of instrument they are capable of measuring the AC signals also. Okay, so similarly the electrostatic instruments, I am mentioning that it can be used for measurement of AC voltages. It means that the deflecting torque will be somehow connected to square of voltage. We'll see that later in this course. Okay, so the principle of working is very clear, that this will work on force between two different charge plates, means they are working on Coulomb's law, right? So when a voltage is applied between the two conductive plates, simply you can say that charges are induced on the two plates. Okay, electrostatic force of attraction or say repulsion is produced, and this force causes a mechanical movement which is indicated by the pointer. Okay. So, for example, in this case you have a linear motion, and with a moving plate, if I have attached a pointer, for example, say I am attaching this pointer over here. Okay. Alright. So, this is the pointer and this is the scale. Okay. And of course, this is kind of linear motion, so it is a little difficult to predict, but then also you will have certain movement of this pointer on the scale. Okay. Of course, we will see that rotational motion is required for the electrostatic instruments also, but this is just for example. Okay. So, these forces between them, be it repulsion or be it attraction, they will cause mechanical movement of this pointer, because this plate is also moving mechanically. Alright. So, the electrostatic instruments operate on the principle of electrostatic forces, as we have seen between the two charged plates, when a voltage is applied between them, and that is how it is connected to the Coulomb's law also. Okay. So, the voltage to be measured is applied between the fixed plate and the moving plate of the instrument. So, now there is a voltage which is under measurement that will be applied between the two plates, the fixed plate and the moving plate. We are calling this moving plate, earlier also we have used this terminology, we are calling it a vane. Okay. So, you are applying a voltage which you are trying to measure between these two different plates. Okay. Now, due to the applied voltage, opposite charges are induced on the fixed and moving plates. Because of this, electrostatic force acts between the charged plates. Okay. And this force produces in turn a deflecting torque on the moving plate. Okay. We will see this in more detail sometime later. Okay. Now, when you have this torque acting on the moving plate, the fixed plate remains at the stationary position, and the moving plate will rotate, which will carry the pointer along with it, of course, because of the electrostatic force. Okay. The moving system continues to rotate until it is balanced by the spring. Okay. And you know that the spring is providing a controlling torque. Okay. So, at that a moment of equilibrium, you have the deflecting torque equated with the controlling torque. So, at this position actually we have seen that the pointer will stop. Okay. And that is what the function of the spring is here. Okay. So, there are two different ways in which the force can act. Okay. So, let us try to understand the two ways. Try to understand the first case. Okay. The instrument consists of only two electrodes which are carrying opposite electrical charges. Okay. So, I am mentioning this since the initial slide, that there can be cases where you have more than two plates, but right now we are considering only two plates like this. Okay. So, the instrument consists of two electrodes carrying opposite electric charges because of the potential applied. Okay. One electrode is fixed, as we have seen earlier also, while the other electrode can move. Okay. When an electric potential is applied, electrostatic field is established between the electrodes. So, when you apply a voltage, there is a electrostatic field between the two electrodes. Okay. The resulting electrostatic attractive forces act between the oppositely charged electrode, as you can see in this case. So, you have these two plates having negative and positive charges, and there is a force of attraction between these two plates. Okay. Now, due to this force, the movable electrode experience a displacement towards the fixed plate. So, this can't move. So, this plate B will move towards plate A. Okay. Now, the magnitude of attraction between these two plates will depend on number of parameters. This will depend on the applied voltage. In turn, of course, it will depend on the charge induced. Okay. It will also depend on the electrode geometry. Okay. It will also depend on the separation between these two plates. Okay. And also on the dielectric medium. So, in turn, if you see, we are trying to, or we are reaching a different concept altogether, that is the concept of capacitance. Okay. So, all these things, if you see, applied voltage, the electrode geometry, separation distance and the dielectric medium is also governing the capacitance between these two plates. So we know that a parallel plate capacitor, okay, C is given as epsilon naught, or say epsilon for example, okay, I am considering certain dielectric material, okay, and A by T. So A will be depending on the geometry, okay, the separation distance is this and the dielectric material is governing this constant, okay. So we are now talking about this electrostatic instrument in terms of capacitance, alright. Now let us see the second way, okay. This was a simple case where you have only two different plates, okay. Now you may have again the similar configuration, okay. Now on application of voltage, if you have say multiple plates, okay, you may have electrostatic force of attraction, you may have electrostatic force of repulsion, or you may have a case where you have both. You have between say two plates you have attraction, between two plates you have repulsion, okay. So you have all the cases. So on application of voltage, the electrostatic forces of attraction, repulsion, or both can act between the electrodes, okay. Now these forces give rise to a deflecting torque on the movable electrode, and the deflecting torque result in again in a angular deflection of the moving system, okay. Now in both the configurations, the arrangement is electrically equivalent to a variable capacitor that we have just talked about, okay. So application of voltage results in a electrostatic energy storage in the electric field, and the movable electrode experience a force or torque due to the variation in the capacitance position, or you can say that the electrostatic energy which is stored is getting modulated, okay. The system tends to move the movable electrode towards the position corresponding to maximum capacitance. Please note that this position of maximum capacitance is actually the position of minimum electrostatic energy gradient, okay. Now this tendency produces the deflecting torque or torque acting on the moving system or the plate which is free to move, okay. We know that if the capacitance between these two plates is C and the voltage applied is say V, the stored energy in this system can be given by the formula this W is equal to half CV square, where this C was the capacitance and V is the voltage, okay. Now using this stored energy, let's try to see the force and torque equation, but since we have this linearly moving plate B, okay, we will see it in the linear motion first and then we will try to figure out in the rotational motion. Of course, the arrangement of the plate will be different, we will discuss that, okay. So please note this energy equation, we are going to use this energy value regularly in this class, okay. Now consider this linear motion now, okay. Plate A is fixed as we have already done, okay. Plate B is movable, okay. The plates are oppositely charged and this plate B is getting balanced by a spring which is again connected to a fixed point. So B is moving, means this spring will stretch itself to bring it back to its original position, okay. So plate A is fixed and B is movable, okay. Now let a potential difference of V be applied to these plates, okay. Then a force of attraction exists between these plates and let this force of attraction between these two plates is F Newton, okay. Now plate B moves towards A until the force F is balanced by the spring, right. Till that position it will move, we have already seen this, okay. The capacitance between the plate is say C at that moment, okay, and the stored energy we have already seen is equal to half CV square for that particular time, okay. So the stored energy is half CV square in this kind of system, okay. Now let there be a small increment dV in the applied voltage, because this voltage is what we are trying to measure, okay. Now the plate B will have small movement dx towards A, okay, and say this is now the current position of B, okay, and say this distance is dx, okay. Now this dx deflection or the movement of plate B is happening because there is a increase in voltage from V to V plus dV. Alright. When the voltage is being increased, a capacitive current will flow, and this capacitive current can be simply given as I equal to d by dt of the charge Q. Okay. And we know that the stored charge in this capacitance Q is given as C into V. Okay. So in this equation 1, let's replace this charge Q by this CV. Okay. So we have this current as d by dt of this CV. Okay. Since we have increased this voltage by V, I am not taking it constant right now. Okay. And then I will be written as C into dV by dt plus V into dC by dt. Okay. I am calling this as second equation. Alright. Now the input energy, which is the electrical energy, can be simply given as V into I into the time period, say delta t, okay, or dt. Okay. So the input energy equation I can write as VI dt, right, and this VI dt will be equal to, this was my I value. If I multiply this with V into dt, okay, I will get the energy. Okay. So V dt into I, right, or I can say VI dt, okay, and say I am multiplying this V dt on both side, okay, both side. What I will get is the input energy as V square dC plus CV dV. Okay. I am calling this equation 3. The input energy equation is given as this: input energy is equal to V square dC plus CV into dV, right. Now the change in the stored energy will be equal to the final stored energy minus the initial value of the energy or initially stored energy. Okay. This we have also seen for other instruments. Okay. So change in the stored energy will be equated with the final stored energy minus the initial stored energy, or the change in the stored energy can be given as the final stored energy value, which is given as half into the new value of capacitance has increased from say C value to C plus dC. Okay. And V has already increased from V plus dV. So the final stored energy will be equal to half into C plus dC, this value, new capacitance value, say I am calling it C bar. Okay. So half C bar into V bar square, and this V bar is equal to V plus dV. This is the new voltage, because I have increased the initial voltage V by dV value. Okay. And this is the final stored energy, this minus the initial stored energy, which is nothing but the half CV square, the initial energy stored in the capacitive system or the two plate system that we are seeing. Okay. So by simplifying, I will get the change in stored energy value as half V square dC plus CV dV. I am calling this equation as equation 4. Okay. Fine. This we have achieved by neglecting the higher order terms, which are very small as compared to the larger values. Okay. So I can say that the change in the stored energy is equal to half V square dC plus CV dV from equation 4. Right. Now from the principle of conservation of energy, the increase in stored energy is equal to the input electrical energy minus the mechanical work done. Or if I have to calculate the input electrical energy, I can simply calculate as the value, which is the increase in stored energy. If I add the mechanical work done, I will get the electrical energy or the input electrical energy, right. So from all these equations, if I have to equate, what I will do is, this is the increase in stored energy, half V square dC. Okay. All right. So half V square dC plus CV dV plus the mechanical work done. This mechanical work done is nothing but this force F, force of attraction, multiplied by the dx value, the incremental movement of this plate B. Okay. Now this will be equated to the input energy. okay, which is v square dc plus cv dv as we have already calculated. Okay. So the force, if I simplify this equation, can be given as F equal to half v square dc by dx, and this is a very crucial equation and we are calling this equation 6. So F is equal to half v square into dc by dx. Okay. This is the value of the force of attraction that we have achieved in terms of the displacement of plate B, in terms of the incremental change in the capacitance and the applied voltage. All right. Now consider that in place of this linear motion, you have the same system in the rotational motion. Okay. In that case, say consider you have a conductor like this. I am calling this, say, conductor 1, okay, and then at certain distance you have another conductor. Okay. Of course, this one is fixed. Okay. Say this plate is fixed, it cannot move, okay, and say this is attached with a spring and this can move. So it is moving and one plate is fixed, one conductor is fixed, so it is having a rotational motion and they may have area of overlap. Okay, at certain point when they are moving, they will have a certain point of overlap. Okay. So say C is the capacitance between the fixed and movable plate. The same thing is shown over here. Okay. You have a movable plate and you have a fixed plate. Okay. Say C is the capacitance between fixed and movable plate. V is the applied voltage. C is a function of angular displacement theta. Okay. Or you can simply write C as C theta. Okay. Now when the movable plate rotates slightly by d theta, the capacitance will change by, say, dc. Okay. Now the stored electrostatic energy will also change because this value is changing. Okay. Now this change in the energy appears as the mechanical work done by the torque. Okay. Or simply you can say that the mechanical work in rotation is equal to the change in the energy that we have seen in case of the linear motion also. Okay. So say mechanical work done in rotation, I am calling this dW, is given as the torque Td into the d theta value, the rotation of this plate, okay, the slight rotation of the movable plate. Okay. So again I am calling this equation 7. Okay. So dW is equal to the deflecting torque into the d theta value. Okay. Now from energy balance equation we can simply say the work done or the incremental work done will be equal to the differential of this energy, the stored energy, half Cv square. Okay. I am taking it constant, this V value. I can simply write that dW is equal to half V square into dc. Okay. So I am calling this equation 8. All right. So now equating the mechanical and electrical work from equation 7 and 8, the equation 7 which was dW as Td d theta and this electrical as half V square dc, I can simply write that Td d theta is equal to half V square dc. Okay. And if I divide both sides by d theta, I can say that the torque equation Td, the deflecting torque, is equal to half V square dc by d theta. Okay. I am calling this equation 9. This is the equation for the deflecting torque. Okay. Td as is equal to half V square into dc by d theta. This equation is very important for the electrostatic instrument. Okay. Now you can also consider this or you can also reach to this particular equation from the discussion of the linear motion that we did. Okay. The intention of the discussion was simply to bring this linear motion or the discussion of linear motion into the rotational motion by simply replacing force with torque and similarly replacing the dx value with d theta value and so on. Okay. So if you recall, we have already discussed for the linear motion of the plates that force F is equal to half v square dc by dx. Okay. So we can write an angular displacement theta in place of the linear displacement x, okay, from this equation only, and the deflecting torque Td in place of force F. Okay. So in that case also, by simply replacing all these value, this F by Td, all right, this v is same, and this dx by d theta, okay, I can simply write as deflecting torque as half v square dc by d theta. So this is my deflecting torque, okay, and let me name this equation, all right. So we have already named it as equation 9. So this is our torque equation, okay. Torque equation we have also calculated for other instruments also, if you remember, all right. So now we have a deflecting torque equation. What we have to do is we have to equate it with the controlling torque. Okay. So if the instrument is say spring controlled, which it is, we have already seen, okay, or has a suspension, control torque can be given as Tc can be given as k into theta, where k is the spring constant and theta is the deflection, right. So if I equate this equation 10 with equation 9, Td is equal to Tc, okay, or I can say that this k theta value is equal to the half v square dc by d theta, okay. By equating this, I can say that this theta is equal to half v square by k into dc by d theta, okay. This is equation 11. It is very clear from this equation that the deflection theta is directly proportional to v square rather than being proportional to any other factor of v, okay. And this is why, if you remember, in the initial slide I have claimed that the electrostatic instruments can be used for not only measurement of DC signals, but they can also be used for the measurement of the AC signals, okay. So this is all about the deflection of this electrostatic instrument, and they comes in various configurations. So they are classified based on their construction and application, okay, and all operating on the principle of electrostatic attraction is there. You do not have any other option because these instruments are electrostatic tools. So they can be of various type, but the principle will remain similar, okay. So based on the arrangement of this disc and plates, you have three different type of electrostatic instrument. You have attracted disc type instrument, you have quadrant electrometers, and you have multiplate electrostatic instrument, sometimes also known as multicellular electrostatic instrument. And the configuration of all these tools are shown in this figure. You have this is a typical attractive type disc type instrument, and this is a simpler version of a quadrant electrometers, and this is a multicellular type where you can see multiple plates, okay. So in the attracted disc type instrument, two parallel metal discs, one fixed and one movable, attract each other when a voltage is applied between these two plates, okay. The one that we have discussed, and of course the control is provided by the spring in all the cases, okay. These are a very simple arrangement of the instrument that we have just discussed, and they can be used for measuring very high DC voltages, like even in few kVs, okay. And they are very common in our laboratories, okay. The second kind of instrument is the quadrant electrometers, where the torque is produced due to the electrostatic force between charged quadrants rather than the spheres, okay, or discs, okay. And you have different quadrants, you can see this, okay, and a suspended vane or a needle, okay. So they are used for low voltage and low potential difference measurement, and they are very common for the calibration purposes, okay. Then you have multicellular or multiplate type of instrument. As the name suggests, they have different multiple sets of fixed and moving plates, which increases the total electrostatic forces and the sensitivity of the instrument, and they can usually they are avoided for measurement of low voltages, and they can be used mostly for the medium and high voltages measurement, and they are common in the electrostatic voltmeters for both AC and DC measurements. Okay. The damping in the electrostatic instruments are provided by the air friction. Okay. The moving system is basically attached to a light aluminum vane or piston, as we have seen in other instruments where the air friction damping was used. Okay. The vane moves inside a closed air chamber similar to the one we have seen earlier. Okay. When voltage is applied, the moving plate starts rotating due to the electrostatic force, and the attached air vane moves through the air which is inside the chamber. Okay. And this air is actually providing a opposite force to the motion of the vane, which is basically producing a damping torque. Okay. So this damping torque is basically proportional to the speed of motion. So if you increase the velocity of the moving system, the damping torque will also increase and will try to minimize any oscillation at the end point. Okay. The pointer comes to rest without overshooting at the final reading, as which is the case in case of most of the air damping systems. Okay. The sources of errors in these electrostatic instruments can be various, including the extra stray capacitances in the instrument. Okay. Mechanical frictions can lead to errors or erroneous results in the measurement. Okay. Temperature variation is one of the major factor because of which you see erroneous result on a electrostatic instruments screen. Okay. And they also suffer from ambient conditions like humidity and other things. Okay. So you should have provisions to control all these things in a electrostatic instrument. Okay. This instrument have a non-linear scale because again the deflection is directly proportional to V square, as we have seen from equation 11. Okay. So when you have this non-linear scale, theta is directly proportional to V square, means that the scale in the lower readings are very crowded. Okay. And in the end you have a expanded scale or measurement marks on the higher side of potential. Okay. The advantage of these instruments is like they can be used for measurement of voltage. Both kind of voltage basically you can use it for measurement of AC voltage, you can use it for the measurement of DC voltage. Okay. They have high accuracy, magnetic interferences are nil. Okay. The power requirement is not very high in this instrument, and the frequency dependency is minimum or nil. Okay. The disadvantage is like they have a non-linear scale or non-uniform scale rather. Okay. So some of the instruments, some of the categories have low sensitivity at low voltages, and the construction is little bulky. Okay. And they are affected by the stray electric fields. Okay. Because this is a capacitive device. Okay. They can be used for high voltage measurements as well as for low voltage measurements, but usually it is preferred at medium and high voltages. Okay. They are useful for power system testing and the calibration of voltmeters. Okay. So I hope that the electrostatic instruments are clear to you. Okay. In the next class, we will discuss about a new instrument which is say rectifier kind of instrument. Okay. So we will be using a rectifying tool to rectify the AC value to DC value, and if you are not aware of what is rectification, we will discuss that also. Thank you.